ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ 2008లో స్థాపించిన కళాశాలలో MBA, NAC A గ్రేడ్ మరియు ISO సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ త్వరలో అటానమస్ కాబోతోంది.
2014లో ISO గుర్తింపు, 2015లో రాష్ట్ర ప్రభుత్వంచే A గ్రేడ్, 2016లో NAC A గ్రేడ్, ఇప్పుడు NBA సాధించిన సంస్థ శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ.
I got a request from Mill asking me to make a video tutorial on how to make a simple counter in VHDL and make it compatible with the Basis 2 board and make the specific pin definition file, compile it and program it to the Basis 2 board, which contains a Spartan 3A FPGA. So let's get started. To get started, you should open the project navigator. After installing the Xilinx ICE development chute, you should have this project navigator. So double click on that to open it and give it a minute to open, and as you see it has opened one of my previous projects, so I just close it. Then to create a new project, you go to File and press New Project. Then here you're going to type in the name of the project. I'll call this Counter App, and then specify the place where to save this project. I'll save it under this Basis 2. Then you press Next. On this page, you're going to specify the FPGA chip or the CPLD, and I'm going to choose the Spartan 3E and then the XC3S100E, which is the one on my Basis 2 board. Then as the packaging, you have to choose the correct one. I've got the Basis 2, which contains the BGA packaging, which is CP132. The VQ100 and the TQ144 is both Q flat pack, which is SMD mounts, while this one is an BGA. So select that, and for the speed, it actually doesn't matter that much in our slow counter application, but you should select the correct one if you're going to make larger applications. Check these settings, as we're going to program in VHDL and not Verilog. This should be set to VHDL, and the others, this should only be one if you're using the free edition, and this is the simulator, which we are not going to use. Then press Next and press Finish. Now you will have your project, and we are going to add the VHDL file. We do so by right-clicking on the chip name up here in the hierarchy and press New Source. Now the new source wizard will be shown, and we are going to select the VHDL module as we are going to program in VHDL. You could also choose the Verilog module if you're going to program in Verilog, or choose the schematic if you would like to make the program as a schematic. But we choose VHDL. And for the name, it doesn't matter. It should be something simple. And as I do a lot of microcontroller programming, I like to call this main. On the next page, you'll be asked to type in the different port names, but this can be done in VHDL too, and I prefer to do this in VHDL, so I'll just press Next, and then you press Finish. Now you will get the template of a VHDL module, and in the top we have the libraries we are going to use. Currently it's only the logic, but we are going to type in and use two other libraries. Down here we have the entity, which is the top entity for now, and then we have the architecture of the VHDL module, which is where we're going to type in if we have any signals for this specific module. And down here, after begins and between begin and end, we have our VHDL code. So let's get started programming our counter module. Okay, so let's get started. As you might notice, I've decided to start and stop the recording. If something happens, the video won't be lost. So that's why. But let's get starting programming the VHDL file. To start with, we are going to define the ports, the inputs and outputs of our VHDL module, and we do so by between the entity we type port, and then we need, as we are going to make a counter, we need a clock input, and we are going to use the one on the basis 2 board, which is a 24, 50 or 100 megahertz clock. So we are going to make a clock input as a standard logic. Standard logic is a normal single unit input or output. Standard logic just defines a single bit. Then we write a semicolon to end the line. The next one is going to be our outputs, the LED outputs of our counter, and we write. I decided to write a vector. It's called in VHDL language, which is in microcontroller language an array. So we write LED 0. Let me see. No, sorry. Out standard logic vector, and we have 7 down to 0 because we have 8 LEDs, and we are counting from 7 to 0. Right. Then I'm going to have a reset button too, which is also just going to be one of the inputs. I think I'll place that up here. Reset in, and again, it's a standard logic. Right. Then we're going to close this port definition, and we have to take care of that the last line in the port definition mustn't contain a semicolon. So now this port has been closed and we've finished defining our inputs and outputs. Then we go to our architecture, which is where we're going to define, as I will call in microcontroller language, our local variables. And we do so, I'll make a counter here, the counter variable. And we do so by first writing signal, which means it's a variable. Signal is a variable, so we write signal and counter, which is going to hold our counter value. And again, we write a standard logic. Standard logic vector 7 down to 0. Right. Then we got our counter signal, and we can start programming the actual FPGA VHDL code. So now for the actual programming, VHDL programming, we go to between the begin and end, and we are going to make a so-called process, the counting process. In the FPGA, we can make several processes which are going to run besides each other. Yeah, kind of like a multi-threaded processor. But we are going to make the counter process, so I call this counter process. And you should make a colon and then process, and we're going to take care of the clock signal. So this process is going to use the clock signal as a trigger. Then we write begin for the process to begin, and now we are actually in the process. To start with, as this process is going to be triggered by the clock, it is going to count every time the clock ticks. We're going to write if clock rising edge of the clock. I remove this. Then we're going to do something. But again, we have to take care of that the clock signal is actually a 50 megahertz signal. So if we're just going to use this signal, the counter would count, of course, but we wouldn't be able to see the actual counts. So I think we'll make a prescaler. To make a prescaler, we make a variable to hold the prescaler value. Again, it's a vector, and this time it's going to be a big vector. I think, if I remember, 22 would be enough. So now we have a prescaler vector which can count our clock ticks, and then count to, for this sake, count to 50 million, and then it should count 1 in our counter. So now we go to when we have checked the rising edge. Yes, great. Then we check if prescaler is less than, and then I'm going to type in the binary representation of 50 million. So I'm going to grab my calculator. Oh. There. And type in 50 million. And get that as binary. Now we got this as binary. We type it in between two marks. What's like those called? Anyways. And then, if the prescaler is under 50 million, then it should add 1 to the prescaler. And we do this by writing prescaler and an arrow. It puts it into the prescaler. Prescaler plus 1. And remember the semicolon. So if the prescaler is less than 50 million, it should add 1 to it. If it is over 50 million, it should first off reset the prescaler, and instead of writing a lot of zeros, you can write others, an arrow, and 0. This would write zeros into all the vectors of the prescaler variable. And then we should, of course, as it's our counter, add 1 to the counter. And end this with end if. And again, end the next one with end if. And end this one with end process. Great. Now we made our counter process, which is both a prescaler and a counter process. It counts the ticks, the clock ticks, counts up to 50 million, which is 1 second, and then it adds 1 to our counter. So for every second, our counter will increase by 1. Now, we're going to make a static definition of our counter variable, as we would like to have this, as I would like to call them, local variables, to be on one of our output variables, output definitions. And we do so by writing. It's actually pretty simple, because this time, the size of both our LED is the same as the size of our counter. So by writing this, the LED would be directly connected to the counter variable. So what is in the counter variable will also be in the LED variable. The problem, or not the problem, but then you might ask, then why don't we just simply up here write LED should be LED plus 1? That we can't do that, because in VHDL you can't read variables definitions which is written as out, though signals can both be read and written to. So that's why we do like this. make a signal, and we connect the output to that signal. So now we actually have a counter, but we haven't used the reset yet. So let's add, just before this rising edge, let's add if reset is equal 1, then it should reset both the prescaler value and the counter value. Whoops. Else it should do this one. Great. So now we got the reset, and we check if the reset is 1. Then we also have to remember to type this in our trigger values, as if the reset is going high, this should be in this one too. Okay, I think about if we should move that reset vector, reset code, sorry. Yeah, let's move that into the clock process. Then it would only be checked every single clock cycle. So we just move it into here instead. Great. Like that. Got it. So now every time it ticks, the clock ticks, it checks. If reset is high, it resets. If not, it counts the prescaler until it counts to 50 million. And when it has counted to 50 million, it sets, it increases the counter variable. So that's it. And we should just, because we are using plus and yeah, plus only, we are going to include one of the libraries called IEE, Standard Logic Arithmetic. And you're ready to go. You should now press the you could directly press the generate programming file, or you could start with synthesizing the diagram. The generate would do all the steps. So I pressed the generate programming file. Now at the bottom here, the generation output would be shown, and any errors would be shown too, which is pretty odd. Oh, sorry. This no. We might have to write use IEE standard logic unsigned all. Let's see if that works. Great, it did. Yeah, that was one of the missing libraries. The unsigned library describes every number. If we write a normal 10 type number, decimal number, this would be unsigned. It's how it is generated in the system, in the logic system. Okay, synthesizing went well, implementing went well, and now we're just waiting for it to generate the bit stream. The bit stream is the stream we're going to program into the FPGA. But then you might think, wait, but we haven't defined the outputs and inputs for the pin numbers. No, you're right. Let's do that. Okay, so now it finished synthesizing and implementing, and actually also generating the programming file. But we're missing to specify the input and output pin numbers of our clock, reset, and LEDs. So for now, it has actually generated a programming file, but this programming file is generated and the inputs and outputs are just chosen from the available. We can see which inputs and outputs are chosen by going to Design Summary and to the Pinout report. In this view, let me make this a little bigger. In this view, we can see all the pin numbers of the FPGA and to which those are connected. This is our VHDL signal names. You can see that LED 0 is connected to A13 and our clock, yeah, it's gone. But this is not what we want, because this is just randomly chosen. So we are going to make a pin definition file. We do so by, again, like we added the source file, we right click the chip name and press new source. This time we are just going to select implementation constraints file instead. And for the name, yeah, it doesn't matter. I like to name it pins. Press next and finish. Now we are in the pin definition file, which is also named .ucf constraint file, and we are going to write the net names. So we write net, and for our clock, this is going to be connected to location, and then we're going to write the location on the chip, the pin name. And as we're using a VGA, this consists of a letter and a number. And actually on the Basis 2 board, it's pretty easy to see the connections because they're written in parentheses. So I can see for the M clock we have it is connected to B8. So I write this. Then we're going to write the definition for the reset, and this is connected to, I'll just take the first button 3, it says on the board, it is connected to A7. Then for the LEDs, we are going to specify each single LED's connection from the vector, and as we have 8 from 0 to 7, or in VHDL language from 7 down to 0, we are going to specify this by writing LED 7. This is the 7th LED. If we have written LED 0, they will be the first. So we take LED 0. This is connected, I can see LED 0 on the board is connected to M5. Alright, now we got our pin definition file, constraints file, so let's close this and recompile, resynthesize as it's called, the project. Click on the VHDL file and you'd notice that now a plus has appeared. If you click the plus under this VHDL file, you would see the constraint file. So let's resynthesize and now re-implement actually, because it has already synthesized, but we just press generate programming file. Okay, well now we got our design completely generated, and we can go to check that the definitions are correct in our pinout report. You can see that clock has been applied to B8. It was also what we wrote, and reset to A7. This is also correct, and the LEDs as we wrote in the definition file. So this is correct. So we are actually ready to program our Basis 2 board now. Now that the bit stream has been generated, you should go to the project directory, which is here, the count app, and you should see a main.bit file, or if you name your project different, the bit file should be here anyways with the project name. We have our bit file here, and this is the file we're going to program. So I'm going to, when the Basis 2 board has been connected and you have installed the adept chute, you should open the adept program, and in there you should see. Whoa! I have to turn this on. Initialize. You should see the Basis 2 board up here, and when you turn it on and click initialize, you should see the FPGA and the serial PROM. We're just going to program the FPGA itself. Remember, the FPGA is a volatile storage, which means it forgets, it doesn't save your program. It's like RAM. When power is off, your program will be lost if it's not saved in a PROM, which can save your program and load it into the FPGA at startup. But for now, we're just going to test it. So you click Browse, and you're going to find the project. Where we saved it, and you'll see the bit file. Double click the bit file, then it's going to warn you about the clock. You just press yes, and then press program. It asks you again if you're sure to confirm, and you press yes. Programming successful, and you'd now see the LEDs blink. Sorry, you would actually not see the LEDs blink, because we made a mistake in the VHDL program, and we'll all learn by that. As I told you, I thought 22 or actually 23 slots would be enough to store this and to store this prescaler and count to 50 million. It isn't. If we count the bits here, there is 25, so we would at least need 24 down to 0, which is 25, but to be sure, I'll just write 25 down to 0. Now, generate the programming file once again, save, and generate, and wait for it to finish. But to be sure, I'll just write 25 down to 0. Now, generate the programming file once again, save, and generate, and wait for it to finish. Now it is finished. Go to the file, press yes, and program it. Now you'll see the LEDs blink and count by each second.